First half of the day we will have the use of these codes in practice, like how we have done in Hadoop, and we'll probably go over some of the concepts that we learned from yesterday also. So on the local regenerative code and regenerative code, I mean we don't use any regenerative code in our Hadoop one, so it will be mainly Reed-Solomon code. So purpose of initially to actually just to make sure that before we start the demo, we understand about the kind of code is used, because I was interacting with some people yesterday, and people still had doubts about what's a code, what's a code symbol, what's a code word, and how code words are really represented inside the Hadoop one. Okay, can I see that everything this is clear, especially in Reed-Solomon code? Okay, what I'm saying is taking an example like a big file, say 64 MB, and then it's all represented as a blocks in Hadoop. We had an idea about how blocks are employed in Hadoop. That's a different point, but let's say we look at the blocks, and if you treat them as a sequence of bytes, okay, this block will be it will be sequence of byte, and they will be kept at the different nodes. Okay, now the coding comes in the way stripe interacts with this block. Okay, so with the Reed-Solomon code, we only have a stripe of just a horizontal stripe, that for every node 1 byte is considered. Okay, is that clear? That idea we talked about that one. So I'll go over some of the codes employed in our work, and then we'll also look at the actual context. So we were trying to do something about how these practical codes behave in a setup, like a topology, and we try to do, but it depends on how we do the demonstration and how much questions you have on that to understand that feature. Instead of that, we first of all we'll first understand from coding theory point of view what are the codes, then we'll go and look at Hadoop as a RAID, how does that happen, and then we'll fill in the gaps required. So it's just, for example, we consider here is a 10.4 RS code which encodes here. So have been in my lectures on Reed-Solomon code, we had a generator code representation. So we have take information bit. The generator matrix is basically k by n matrix. Whereas on the other hand, when we described in a distributed system, we just simply distribute as some kind of a place marker for the code symbols. So you have a code word of length 14, then you can think what has been mentioned is a kind of place marker for each one. So for example, when you have a code word, first symbol from the code comes from here, second symbol comes from here, and so forth. Okay, this idea is clear? So really from that's one in the LRC what they want is we want to put all of them in kinds of with the locality information, in sense the domains where the nodes can easily access each other. So that's why the codes with locality comes into picture. But on the other hand, with Hadoop Reed-Solomon code structure, what we have is basically simply the blocks, and the blocks can be you can assume it as a same thing can be elongated from this. So this is taking one code, making it apply for a 164 MB. Is that clear? So I mean, if you can have some kind of doubt, what I can say is that we will just take this as a message. For example, here x0 n up to x10, and you can have a generator matrix that has a identity for first 10. Then you have P0, let's say this is 11th, so let us say this is 0. You can say P01, P01 up to P02, P03, P04, and P0. Okay, it's just like that, 1, 2, 3, 4, and then will be 1, 1, 2, 3, P02 and P04, P14, P14, and so forth up to P10 something, yeah? P9, that all the parity equations. So you can see that when this is multiplied, you get in the first 10 positions you get that one, and then parity will be computed as a linear sum of this. Okay, and he told you this is what is actually uses in the RS thing, and they optimize the code to do it properly, because when the decoding is running, what will happen is that you download. So let us say, how do you get the block from for our operations? If the block is already, let us say, information block is on this particular node, really the fetching will be simple. It's just get that node. So you don't need to do anything. So if you want to access data corresponding to that block is available in that node, so there is no need to worry about it. So it's really the accessing data from the Reed-Solomon code is simply reading, nothing more. So really the performance is based only on the reading. Only problem happens when there is when the node goes down, as a new node now has to create it. Now new node has to create, let us say, 1, then it has to download at least 10 other nodes to do it. So sometimes it is possible to, for example, as in the hitchhiker code I mentioned, it is possible to arrange let us say this parity to be simply the sum of all parity, which means that you now start downloading all these blocks, okay, and many things, because of the pipelining structure, you can start decoding immediately after you have obtained, say, part of the chunk from these nodes. So there will be some kind of a once the data decoding process starts, there will be some kind of a so there is a decoding process start, that I think once it will be probably clear when we do the thing. So let us say decoding pass as a time here, then it at this point send a reading stream from reading stream as some kind of an idea, and then after that we start getting a lot of small reads. So now a stream reading means it has to get 64 MB, and obviously you won't wait until all the 64 MB is downloaded. So what you do is you first so the whole process, which Aaron will show, it can be it will become much obvious. Then what happens is that our system will start sending out read for everything. So this happens for every node. So as soon as you have a sufficient information, so there will be a block for the decoding until something's arrived, then this can happen parallelly. So in fact, actually as soon as, let us say, 10 chunks of other things are available, the decoding can start. The decoding, let us say, is one node. It's very simply maybe just a XOR, if it's depending on the generator matrix. In that case, the time gets absorbed while it is doing other things. So really actual computation of decoding itself, linear combination of things, is not a big problem for us, correct? So that's what will happen with this, but this is the structure of the RS code that we employ, okay? So once you have done there, then that's what we do. That's one code we do. And the second one is the Sorbus LRC code that we mentioned yesterday. So it has 10 nodes. Basically it is it works in some sense. It was actually, there was RS 1014 code was already there, and you wanted to make that more efficient, and these people thought about, say, adding local parities for every 5 node and this 5 node, and finally for this also there is another thing added. So if you look at it now, there are additional encodes 10 source block dates and 6 parity blocks. So this is 4 plus 2, out of which 4 parities correspond to normal RS coded and 2 remaining are local parity blocks. So it's generally 16. But sometimes it's used, this is not always used. So this is an example of just a 14, 10, 2 code. So that has this is 5 code. Sorry, this is actually local parity, 6 parity blocks. Is that clear now here? So you can see that there is 10 plus 14 plus 2. So this one is sometimes is actually not employed, only when that comes with the parity ones. Okay, so this is the LRC design, and we found that the LRC design, for a same storage area, LRCs will help you with nearly 50% improvement in the bandwidth, or for same bandwidth it will add some additional storage. So it can do, I gave the thing yesterday, so we may go over if there is any doubt in that one. Okay. Is this idea is clear? This is so the LRC is also the same thing now, except that now the Hadoop system knows that these 6 blocks are there, and so really the decoding will only, if there is one node failure, the decoding will involve only these 6 nodes. So basically only 5 basically, 3 plus 4 plus this one, that ensures you to get that one. Only when there are more than one error happen, then you need to do like a Reed-Solomon decoding. But for usually single error, single node failure is quite rampant. I mean it's quite, that's what mostly happens, and then you can only use the locality to do this. So and then what we do, the other one code, so obviously when we tried, so we tried initially just making sure that RS code works properly, and also we've been able to allocate nodes at different points in geographical topology. So normally what happens is, if you have a specialized a cluster working, and if all the nodes are at the same place, then you can have probably better solutions. But the problem is that now when you have different nodes, say assume that you get 3 different localities. The one could be Melbourne, other could be Perth, and other could be Brisbane. And when I sign up for those kind of devices, I can get devices elsewhere. So I may have certain disk here, certain disk here, and certain disk here. So when you are writing a file, and when you have certain file, what we have to do is basically we have to identify the nodes, and especially let's assume that we only have a Reed-Solomon code before, then our job is to choose where should be the first node should go, and where. For example, how many nodes I throw in here, how many nodes in throwing here, like that. So if there are 3, and if I want a reliability, because I don't want, let us say, all my nodes in the same location, then I might distribute them. Okay, so that will be 4. So this is one aspect. So 12, another 2 maybe you throw in 5, another 2 maybe here, so make it 2 extra here. And so then you can actually, some of these things you can actually compute the cost between the nodes and estimate, say, what happens. So for example, you could then you can think of, for example, you can have a clusters. So for example, I have a cluster of nodes. Maybe I throw in all nodes into one cluster. That's one type of configuration. Then I can like the equal distribution is another variety, and some may be equal. So these considerations that some nodes should be spread in a particular way, it is sometimes not design choice. Like it's not a choice for the code. The code you have no other choice, you have to use it, but the users may have some other restriction. So in doing so, you may have multiple options to actually put them together. So which configuration is better for our work? So you can think of that. That's when, for example, we introduce optimization. So I'll probably go over some part in the next lecture. But when we have a geographically distributed one, so the issues are same. For example, when we have information nodes are there, so if for example it is down, it may maximize for example getting all these ones, right? But on the other hand, the work cannot start without, for example, getting so you need only 5 here, so you need at least another 5 more. So there is no, you have to contact the other two nodes and say assume that this could be, say this could be 5, this could be 2 and this could be 1, okay. Then which you will try to choose, you know, for a node failure, okay. For in this case you may want to choose these nodes, okay, because that it has a complexity 1. But on the other hand, even if you choose all of them for repair, you need to one of them 1, but in this case you might get some complexity. But this kind of situation you need to look for every node, because in our case any node can fail. So then how do you actually describe the cost associated with you know, this placing these nodes? That's not a trivial problem, right? And this is one of the problems that was also discussed when the problems were introduced, and you know, using proper theory we may be able to do that one. That's what we'll see how we do. So the Reed-Solomon code, it's a simple description. The code just goes in the same way. So local Sorbus design basically. So when we started, we had a code from Sorbus, because Sorbus was shown to have a better decoding performance with respect to RS, and so that's why we were comparing. And these were of course tested, the Sorbus, in a real Hadoop Facebook cluster. Then they are all in the same rack, you know, in a data centers. So that way, and so that time the Hadoop actually what it follows is, for example, it can have some placement policies, as you show for the same rack. It adds the one node, the other node, any replica, it just tries to put it in the same node in the same rack. Then the one other one it puts in the other rack, and so the computations happen that way. So, but you know, there sometimes if a rack failures, all the things are failed, right? That time you need to go to the other side. So this Sorbus was actually shown to have a lot of improvement in that paper. So this is the kind of this code, and we implemented that on a geographically distributed clusters in such that form. So we'll give more details when when the problem formulation if it comes, but that was how it was done. That was LRC, and we found that, you know, obviously because some nodes were nearer, it helps, but in some aspects the results weren't that different from the RS. Yeah, so only in some aspects we will come back to that. But of course, when all the nodes were kept in the same node, that was you know, same location, we did observe the Sorbus did better. And so these were actually published in 1 or 2 conferences that we had on that. So as opposed to that, you know, in order to increase this locality, one of the simpler code that I didn't introduce this before, so because we were thinking of practical thing running, so maybe before we go to that we should do this as well. So this multi-XR code, what it does is that basically it's the same thing now. It uses only XR operation. So you can think that now, so here don't think from the coding generator matrix point of view, it's just like a placeholder for every data. So now you can see that it's not now anymore in one row, but it's true, but everything is a node. So for example, data 1 is also a node, data 2 is also a node, like that. Okay. So what MXR does is that it creates both row and as well as column parities. Now what is a row? What is a row parity? Row parity is for every 5 node, you know, along the row, you just take exclusive OR of all the bytes and put it in parity 6. So parity 6 is simply that one, and similarly parity 7 is that, and then parity 1 to 5 are basically column parity. So in this case, if a particular data is available in data 1 and 6, and if one of them is failed, you only need to really contact 2 other nodes. Okay. So when you have an option like that, say even for a 3 node structure, we can actually place some of these groups into the same node, and thereby you can gain some performance advantage. And this is a quite simple code, right? I mean, but still a Reed-Solomon code. You can see that this. So what is the what is the finite field, like the structure of the finite field used in XOR? It's same XOR code. What is the smallest finite field need to represent this code? Binary? Yes, very good. So in fact, in case of Facebook and other Reed-Solomon code, you start with either byte or a, in fact, in the JRASR library we mentioned it is actually GF2 to the power of W varies from 1 to 16, but invariably data centers or systems will use either 1632 or 64, whatever, 8 1632 mostly. Because it matched to the word size, whereas in this case, even though the code is actually a binary code. So in fact, this is also sometimes known as an array code. As you can see that this one is a 2-dimensional code, where what you need to have is basically a matrix, 2-dimensional matrix. So you have a, this is the parity and this is also parity. In fact, in the 2-dimensional code you also have a global parity involving all that, but this is not using it. So in fact, this code you would have probably recognized. So you have this is kind of A, B, C, D, E, F, G, H, I, J. So this is sigma A to C, and sigma, this is sigma, and this is also sigma F, and this will be sigma A F, B, G, C, H, D, I, and A, B, C, D, E, E, G, H, I, J. Okay, see, this is simply added this. These codes were earlier used in 2-dimensional other applications as well, and this MXR code it became famous. I mean, in the sense that it's pretty easy to use, and we found that that gives actually better. But let's look at the performance of this code. What it does basically, it has for every 10 information bit, how many extra bits we added? 7. So it's to go this is slightly more than RS code, because there are 3 more things, but with a little penalty in the storage, we get the performance speed up. In fact, what we got was for this multi-XR code actually performs much better than all other candidates in our example. I'll show you in the results in tomorrow. So, but so let us see how many node failures that this can tolerate. So can it tolerate any 1 node failures? It's quite obvious. So what about any 2? Any 2? So for example, any 2 definitely is true, right? Yeah. Oh, how can you say that? So for example, if let's say assume that it's in any 2 columns, then you can use the corresponding one to do it. If it is in the same column, then that time what can you do? So let's say that's question. Let us say now I have I'll now replace this by number, so easily to two, 3, 4, 5, 6, 7, 8, 9, 10. So let us say this is done. So we have how many reads you have to do to replace that? 6. So 10 at least. I know if I can get these 2, so 10 I can definitely do. Yeah, but how much is what's minimum? Huh? 6? How? So take 3, 5 here. So then you then do it. But the second one you have to wait until first one is decoded before you do. So another concept that's happening in regenerative codes, and this is basically this kind of this is called cooperative repair, or sorry, sequential repair. So when you have more than 1 nodes are failed, I can parallelly try to repair it, or I can repair one and then use this data to repair a second. So, the performance of the code when it is in the serial this way or parallel can differ, and in fact they show that the optimal things happen for each of the definition the optimality things are slightly different. So, the theory in handling that is can get quite complicated. But as you can see the issues come like this, and so in fact I can give out another reference to this. This has been also employed in like a cloud storage, and they use this kind of a card, but they even go about and make the array code, which is something about something like a 5 by 7, I think. I am not very sure. So 5 by 5, and then you have all column parities and also row parities, and including the global one, I think. This has been used, and I will give the reference, and there are, and these kind of codes you can ask actually what are the properties, and that, so there is another branch of distributed code things where they talk about these ones, so which I didn't even touch in the course because there are so many of them. Okay, so this is how we do with the multi XR code. So these are the 3 codes that we have tried, and say so Facebook. So the stripe design I have already talked about. Facebook RS code, Sorbus, LRC, and MXR code. They all ensure stripe as a simple combination of source blocks and parity blocks in a row. So except that even though I have here in MXR code like an array, the stripe for that is still one dimensional. You clear? Because there are some non-trivial coding technologies where stripe can be more than one row. I'll come back onto that one in the advanced code period. But even though here it is true, at least the MXR code is still one row. So for all our comparison, we only use a stripe which is just one row. That means when I have a consecutive blocks, so what does it mean that if I have, for example, a 640 MB block, so one block, first block will be here, second block will be here, third, fourth, and so forth. But the data nodes will know exactly which block is in which data node, and so depending on when the programming is done, it will take care of automatically. So there could be multiple ways to do it, and I think multiple ways of arranging it, but we don't care. So all of them we call, in this case, is basically we will look at the locality groups together. So as soon as MXR code is there, it's actually one whole big row of a stripe. So the stripe is simply here, but we might identify local groups for the code, and then accordingly we will use that to determine where to place them to improve the performance. That's all we do, but that's how we do these ones. Okay. So resulting code is only actually 16, 17, but we do the same. This is the structure design, and so this should be, I think, when that is clear, then when we run now the Hadoop code, that will be, it will become much more clearer. Okay, so we can